we're changing gears a little bit. We're going to get into how to measure water in forests using microwaves in particular, but also a few other remote sensing techniques. And I would encourage you to ask questions straight away. I spare the slides because it's very easy to forget about them if you wait until the end. So I prefer to have an active discussion throughout the presentation. As a child, I imagined that I could see through things, that I would have this X-ray vision just like Superman. And as a grown-up, I have actually learned that it is possible when we're working with electromagnetic waves at certain frequencies. So we will actually start in the end of looking at electromagnetic radiation, how the scattering happens. If we have an incoming wave with some frequency that is noted by the wavelength lambda, and then we have some type of particle with the size r, these will interact with each other. If this particle is very big in relation to the wavelength, then we get something that we call optical scattering or geometric scattering. This is described by this r is much larger than the wavelength. And that is what we typically know as the visible light, where we have a reflection against the mirror or it's coming back. It's also what we know from visible light, where we get the shadow behind, for example, a tree. However, when the wavelength and the particles are of similar size, then we get something called Mie scattering. And now this changes how they interact is a little bit different. Now this is not only passing through or reflecting. Some of it will be transmitted and absorbed, and some of it will be backscattered. So we have a different type of interaction between the particles and the wave. And if we take this in relation to radar or microwaves, this is often the case because in radar, we're speaking about wavelengths of about 1 centimeter up to a meter. So this is the most common range we're working with. It corresponds to frequencies of about 300 megahertz up to 30 gigahertz. And that is, for example, the case we have with branches interacting with the radar waves, where we have a little bit of the similar size. Of course, the branch is not always the same size, but that is in the range we are often working with. However, when we get to the case where we have a wavelength that is much longer or much bigger in relation to the particles, then we get this Rayleigh scattering that we know also from the sky, that is like this blue sky that we have heard about, the most of us. This is causing most of the particles, of the wave to actually go through the particles, so we will actually penetrate them. So it will appear very transparent compared to the incoming radiation. And this is a case when we look at, for example, the needles, or when we use a long wavelength in relation to the tree trunks and the branches as well. So when we're working with a wavelength that is 1 meter, the trees are more or less visible or invisible, like you are transparent. That is correct. So microwaves are affected by both the geometry and material properties, and mainly water. And since we have LiDARs as our golden rule or golden standard for measuring the geometry, you can to a high degree say that we are actually using microwaves as a water sensor. And we will know that water constraints and drought becomes increasingly severe. So in that sense, a lot of the radar-related work and microwave-related work is about waters, how to measure and quantify water. So we have a system called boreal SCAT2, which is the tower-based radar system in Sweden. The boreal SCAT1 was mounted in Remningstorp in southern Sweden until this area was, the forest was destroyed by bark beetles. So I actually had to move the tower. So right now, this boreal SCAT2 is mounted in Svartberget, which is about an hour outside of Umeå, where we're located in northern Sweden. And we did some upgrades. So we call it boreal SCAT2 because now we also have a moving antenna frame. So we can do full 3-dimensional tomography. And we have Shivam Rawat, which is a PhD student from India, who is working with this. So with this tower, we can observe the diurnal cycles, how the tree water content is varying day and night. What do we see here? Well, we see something, a red line. We see something that is a little bit more bluish, and we see a stronger red yellow part here, and then we have blue. Here we have the time in days, and here we have the height above the ground. And the intensity is the intensity of the backscatter of the emitted signal. So that it is more red here, that is indicating that we have a stronger or more like material properties and more water in the canopy that is reflected there. So we get a stronger response from there. That is kind of indicated by this, what we see from the single tree, but in this case, it's actually an average over many trees. Then here we have a section where we don't have so many branches, and that is why we have more blue here. And then we have a very strong ground response. So that is what we see in this. Then it might look a little bit blurry here. We don't see it as a completely straight line. And actually, if we look a little bit more carefully, what we see here are the changes. So if we only look at the changes and only look at the parts that are related to the canopy, we can see how the backscatter varies up and down, day and night, 24/7. So we can really track the heartbeat of the tree, how the evapotranspiration is happening all the time. It's also very much related to the temperature and also to some degree to the precipitation that we'll get into with a few examples. So with this tower, we can measure a lot of different wavelengths, but if we look specifically at the UHF band, which is in between the L and the P band, we can see how this trend is actually correlating very well with the stem radius as quantified by the dendrometers. We can also see how it is negatively correlated with the vapor pressure deficit that we have also quantified. And this is a non-destructive way of like measuring these things. So that is the nice part, and we can do it for a large area for many trees in a very short time. We are doing these measurements approximately every 5 to 30 minutes, depending on what frequency we're speaking about, 24/7. So we have a lot of data for a long time series. We can also do tomography in the sense that we can divide it into what is in the like at different heights levels. We can also see how the ground backscatter that is specifically in the just around zero heights, 0 plus minus a little bit, is following the trends of the soil water content much more than what we hear. These two are related to the canopy we see above the ground. So we can actually separate. They are not perfectly aligning, but the trend is there, and the soil or ground backscatter is following the soil moisture trends much more. We have also mounted sapflow sensors on different sides of the trees and at different heights. For this graph, we have the results from the breast height, 1.3 meters above ground and 8 meters above ground. We have also mounted the sensor that's 40 meters above ground, and I haven't got the results yet. But we see these strong diurnal cycles. In time, they align very well for all 4 sensors. But we see a huge difference if you look at the north and the south side. We also see quite some difference in magnitude if you're looking at the lower part of the trunk or if you go into the upper part of the canopy. And usually this is a delay, time delay, how what is passing through the lower trunk and what is coming to the upper part of the canopy. And this was just to zoom in a little bit because it might be difficult. Hopefully some of you are also watching it directly on the Zoom meeting so you can see it easier. But right now, for example, the blue line here is at the lowest part from the north side of the pine tree. And then we have the red one, that is the south side. So we try to link this together with the branch pattern. And in a related project, we're using LiDAR to identify the different branches and using that as a biometric fingerprint for tracing the single trees throughout the value chain to the sawmill. And in that work, we have derived this type of unwrapping. So by TLS scanning the trees, and then you can unwrap like this. So this is actually the full stem from one side all the way to the other. And these are the branches as you are unwrapping them or projecting them on the flat surface. And this, the number of branches that we see on the different sides, is correlating super nicely with the amount of water that we have in the sapflow. It is still work to be done to quantify this for a publication, but the correlation is very, very obvious. Here we have, this is on the west direction, this is south, this is east, and this is north. So in this case, we have more branches on the south side of the tree, which makes sense, which also makes it to consume more water. And this last one is just the number of branches, a histogram of how many branches, because the number of branches is not necessarily the same as how much branch weight we have on each side. This is how it looks for a Norway spruce tree. It is a bit more messy. The branches are denser, so it's more difficult to have very good delineations of the single trees or the single branches. But for this project that we do for the fingerprinting, we're actually looking more where the connection of the branches are to the trunk and not so much about the branch properties itself. And it works actually quite well for just creating this type of unique fingerprinting. But since I'm trying to combine this with this work about quantifying how much water this consumes, we still have a bit of work to do to quantify the amount of branch biomass to make this. We also see that here the direction of the branches are a little bit different. So as of now, it seems like that we actually have more branches to the east direction and not maximized to the south. But I'm not an ecologist, so maybe we can figure out a little bit more why that is. If we look at time series of the radar backscatter from the tower, we can often see this type of very strong peaks jumping up and down. And that is often the case when it has been raining. So the precipitation is causing the reflective properties to change. That is basically that we're going from, like the floor here is not very reflective, but then you would have a mirror, then it would change the scattering properties a lot. That is basically what happens when we have these rainfalls. So you get a very strong response compared to when it is dry. But now the water is on the outside. So all this work is happening right now at Svartberget in Sweden, which has become kind of a super site for microwave and a lot of remote sensing research. And here we have this IFE SAS tower, where we do a lot of these greenhouse gas measurements, different types of temperature, wind, and so forth, and also other types of aerial measurements, like radiation, like heat flux, and so on. And here we have this radar tower, which is a 50-meter tall construction. And currently we have a P, L, C, and X-band synthetic aperture radar in the system, which allow us to do this fully three-dimensional tomography. Actually, I've forgotten to add the UHF band, which is also one of the bands we do. And it's a multipolarimetric, so we have the different combinations, which is horizontal, vertical, and then you can emit in horizontal and receive in vertical and vice versa. So we have 4 different combinations of doing these machines. On the trees, we have these tree water sensors, where we measure, for example, the sapflow, stand water content, and so on. We have a mobile BRI system. The intention was to have a fixed one in the tower, but the apogee stops producing them. So right now, we're going with a mobile one. We have a ground penetrating radar that is basically looking like a grass cutter that you're pulling or pushing on the ground.
What is the speed?
Photoreflective. Yeah. Check like what Eija was presenting as well from the hyperspectral data. This what is it, 531 and 572 nanometers that you're combining for the synthesis. We have soil moisture measurements, both permanently installed ones, and we have a mobile device, one for G, PR2 device, which can measure the soil moisture at different depths down to 1 meter. And then we have a drone-based radar system that I will soon get into. We have measured the humus layer at different locations within. So you see the thickness, which is one of the variables that we're trying to quantify with these radars. And we have estimated the root biomass using allometric functions and related that to the radar backscatter. And we have, of course, airborne laser scanning, terrestrial laser scanning, hyperspectral, multispectral drone images, and so on. And we measure the single trees. And we are also starting now to work with the GNSS systems, which are the active emitters with L-band radar. So the GNSS system that we use, like a GPS, they correspond to the frequency that we use for L-band radar. They are the same principle, but we don't need an expensive tower anymore. So this is an overview of this area. Where we have here on the right side, we have the tower. Here we have a very big corner reflector, which is 5 meters tall, that we use for calibration of these tower measurements. Then we have this type of big reflector also under the canopy, so we can measure the signal difference when it's going through the canopy, and we have a clear line of sight. Then we have mapped out the line that would and some tree construction. Of course, this is a height model that's from ballistic scanning. And we have measured the single trees, about 1,000 trees within 90-meter sector onto the tower. And then we have added a lot of these drone-based radar measurements, which are tomographic measurements that are shown in this image. So let's jump back a little bit in time and look how it was in Remningstorp when we had the forest cut 1. And the trees that were in front of the tower there were affected by bark beetles. And we could see how close to the tower, this was the last year actually where we did measurements, how the trees closest to the tower were affected and changed throughout the season as seen from the optical camera in the tower. And this is a time series of this area where you have, before we started to build the tower, 2017 we built it, in 2018 we had a really dry summer and did a lot of measurements. And a lot of the bark beetles already came in 2018. 2019, we therefore had to cut, or not we, but the foresters of this area. They wanted to cut the entire stand, and we asked them, can you please wait a little bit with the trees in front of the tower? So we negotiated that some of the trees were left for a while, and they cut the rest of the stands. So we could do additional measurements in 2020, and we see also in 2021 the last effect of these trees that were infested in 2020, and they are all cut down at the moment, so there are no trees left. And what we saw from that earlier work was that we had a backscatter drop, which is basically because the water disappears from the trees and they stop the function. So the signal is no longer backscattered in the tree, so it's basically going through and reflecting away from the sensor. And the 5 dB change that corresponds to an effect of power of about 3 times. So it's quite a lot. And we had an inventory of the trees that were left in the fall of 2020. So now I have marked the different trees according to this inventory person when he could decide also when they were tapped. I cannot really judge if that is so easy to do, but he said that, yeah, I can say that this one was infested last year, this is 2 years ago, and so on. So he seemed quite confident in these statements, but it's hard for me to really say how reliable those estimates are. But if we look at the time series, we can see this changes a little bit over the time. Maybe the very easiest thing is, for example, here in 2019, we can see that it is changing from where we had forest to there is no forest. That is very clear that these shifts are happening. But if we are actually looking just at 2019 for a few trees within the footprint, and then if the record for it, that was also mainly spruce, pretty close to the tower, and we can see at the time series from this was 2017 to 2020. In 2017, these signals are more or less similar. In 2018, this starts to separate quite a lot. 2019, we see how they really go well apart, and that happens already from the beginning of April. So we can see this response at the very, very early stage, and then to some degree it is getting more back to normal in 2020. Jumping back to the tower in northern Sweden, we have also ordered a new thermal camera for imaging the water deficit and drought stress. That is hopefully arriving today or tomorrow. So the plan is to mount it now in November. It is measuring about 7.5 to 14 micrometers. So it's the temperature that we have. It's going to be mounted at a 45 meters elevation of the tower, which will give us approximately 5 centimeter pixel resolution of the canopy. So the hope is that we will have sufficient resolution so we can actually see the different parts of the canopy and relate that to the sapflow sensors that we have at the different heights. And that should hopefully reflect also the change of water at a much faster time scale, the higher resolution that we can get with from the radar. Because the radar is very good at these measurements, but the spatial resolution is lower. That is the like flip side of the coin, that the more penetration you have, the lower spatial resolution. So this is somewhat an intermediate way where we want to do a little bit more. We have also bought a TLS that is scanning this area continuously, inspired by the work from Finland. This is not mounted in a tower, this is from the ground, but it is still giving a resolution of about 1 centimeter, 100-meter range, and the trees in this area are only 25 meters high. So we hope that this will be sufficient to have a good measurements of how the branches are changing throughout day and night. I think that you have been very impressive that work from Finland, and how that's like we will often make this assumption that we have like a branch that are static and that they are only in one way. But it is very obvious when you watch the trees in the winter and the summer that you have a big change. But through that work in Finland, we have seen that it is also changing much more frequently than for just seasons. Anyways, this is just one tower at one location and one forest. So how can we generalize this? How can we make this more like, how can we understand this better? Well, we have this drone-based radar system, which allows us to explore other areas. So the current work is trying to compare what we get from this drone-based radar and the tower-based radar to see if we can actually build on the same principle. So these hypotheses that we have derived from the tower, can they start to be applied with the drones? We can actually measure other types of forest, other ages, other compositions of the species. And one of the unique parts with this is that we can do spiral flight trajectories, and that allows us to do tomography also with the drone. That is completely new. That has not been the case before for many different reasons. A radar-based system needs a very stable trajectory because the antennas, we jump back actually into this. The antennas that we have here, these are P-band antennas. That has been a big issue in the past to carry so big antennas for a radar. This is an L-band antenna, and this gray box is a C-band antennas. They are much smaller. But to actually have this type of penetration, we need the big antennas, and that has been an issue. And moreover, you cannot build so big antennas that you would do measurements directly, but also you need to do that we say synthetic aperture. Synthetic aperture radar means that you're using this antenna that is kind of small. You move the platform, make the assumption that the object that you're observing are the same throughout this path. Move again, do the same measurement again and again. And you combine all these measurements to a synthetic aperture, a synthetic antenna. And that is a way we can actually derive a rather high resolution in terms of radar. I mean, it's still lower compared to many optical systems, but it is what we have for this type of microwaves. And the unique part here then in this spiral flight is that we are varying the height and radius throughout the flight. And that is basically the same idea as we have it as for a CT scanner in the hospital. So we can actually see through, and we can derive voxels of about 20 by 20 centimeter in space at P-band. At L-band, we're about 6 centimeter, and at C-band, 2 centimeter resolution. It's a very high spatial resolution. But we also have these issues with noise and other things in radar systems. So we typically average and say, take a factor of 5 or something, that you're closer to something that is useful. But what we also found out is that we actually see below the ground. So we can actually start to see the root systems of trees. So qualitatively, we see an extension of the root system where it is, we have made this as a homogeneous volume, which is of course not true, but we don't have the spatial resolution to actually delineate the individual roots. So this is an assumption that we right now are doing. And we have Ansgar Jorgenfeldt, which is also a PhD student working on this. We have also carried out one campaign last winter where we were watching snow. That is a very big interest to plan for the electrical consumption of the time, to know where the snow and amounts of volumes are happening and when they are melting. And also because we want to see the different layers to predict, for example, avalanches. This is a little bit at the outside of my research. It is not my main topic, but I'm very interested in snows in that sense. I think it's a luxury that we can can push the borders a little bit, and it is nevertheless frozen water. We're taking some snow water equivalents and density layers, and there is some research since before that shows that X-band radar can be used to identify the different crust layers in snow. But in general, snow is considered to be transparent for radars. So it is usually when you have these melting conditions, when you get more water in the snow, that you can really see these layers more clearly. Okay, still, both the tower is expensive, the drone is expensive. Can we make it even cheaper and more universal to get to any location? This is where we're getting into passive microwave sensing. We have a new PhD student, Gilbert, that hasn't started yet, fully around New Year. We'll get those of you, where we're going to work with passive microwave sensing. And the idea here is that we will have one receiver under the canopy and one receiver outside the canopy. And then we can compare these scattering patterns, where this one will scatter through the canopy, and this is the unobstructed line of sight to the satellites. This GNSS satellites, again, it corresponds to L-band radar systems, so they have the same properties as we can derive, for example, from the tower out in the drone. So in the end of the day, we will actually get a volume like a cone per field plot with properties of, for example, the wood density, the vegetation water balance, and hopefully also biomass and other forest structure metrics. The same idea that we apply just for new equipment. This is a collaboration with the Smithsonian, Harvard, and Yale University in the US. So although we have a little bit of challenge with the political situation, they are very skilled at what they're doing. And we have built these GNSS receivers, where we have 3 of these receivers in SVU, and they have 3 receivers in the US. And the hope is to do some first measurements this winter in the States, and then we're going to do the first measurements hopefully next summer in Sweden. Finally, to round off a little bit, what can we do into the ground and soil? We have a ground penetrating radar system that, I said, you can push it or pull it like on the ground. It looks like a grass cutter, and that is one example of how such a system looks like. And this is a type of image that I get out of it. It doesn't look much for an untrained eye, but these different waves and structures, like the texture, is actually giving you a lot of information about the properties and how they are changing in the ground. And in this specific situation, these kind of curves that are happening here, they are a response of objects lying there. In this case, they are boulders. We also have a very strong border here, like edge. These are marking the borders of man-made grave outside of in Skogfors research forest, like 10 minutes outside of Assoc. And some of the work that we have been doing with the drone for the soil is to estimate the root biomass. And these are some results for pine and spruce trees, where we actually, for the first time, as I'm aware of in the world, to show that we can actually map the below ground biomass with a somewhat linear relationship. I totally agree with that it is not a perfect one-to-one line. And there's a lot of unknowns in this work, because we have to make assumptions about the soil composition and how the wave is refracting when it's going through the soil. And of course, the soil is not a homogeneous layer, but that is the assumption we have to make to get something out of this. But just to find a relationship at all, and actually being able to create a map and say we have more or we have less in this or that area, is a lot of value compared to the people that I have spoken to. In practical forestry in Sweden, we also have this way that, for example, when you cross a mire and you're building winter roads, you have different rules if it is a very deep mire or if it is less than 2 meters, because we have forest machineries that have going through the ice in the winter and people drowned. So if they have more than 2 meters of depth in the pit, you need to take other security measurements into account. So they are very interested in having this type of mapping for larger areas. So this is an overview of these graves that I mentioned outside of in Sava. We have 10 different graves with different soil compositions. And we of course asked for the specific types of soil that we put into this, so we can quantify the effect of different types. But we have also been doing the opposite, of taking these measurements and actually trying to verify that it is what we ordered, so to say, see that they align. And this is a three-dimensional view of how what we have in these graves, just illustrated from the photogrammetric measurements during the construction. And this was from a candidate work that I was supervising. They put this into just a nice visualization. This is one example of how this type of ground measurements look like from the drone-based radar. So the one that we put like push to pull along the ground, that is giving a two-dimensional representation of the ground. But with this drone that we can do tomography, we can actually do these cuts. I don't know if you see it, but there is one cut this direction and one cut in this direction. So the idea is to illustrate that we have a full three-dimensional reconstruction in space. So right now, I mean, we can see that we have objects and they are not super sharp, but we can still make this, or the work is to convert this qualitative in measurements into something quantitative. And that is work that has started quite recently, I would say, with a new PhD student, Noak, a month ago. So some final remarks. Microwaves and wavelengths that are complementary to optical are affected by both geometry and water. But in that sense, radar can be used as a water sensor, given the assumption that the geometry is relatively stable over time. So if not geometry and the water conditions are changing at the same time, we can use it as a water sensor. Yet the spatial resolution is somewhat lower compared to many of the optical systems that we're used to. But instead, we have a higher temporal resolution. That is one of the benefits. Also from satellite-based radars, to get the measurements continuously, regardless if it is cloudy or if it's sunny or if it's dark or it's light, since it's an active emitter. So do you have any ideas for research and collaborations? Please reach out.